Okay guys, let's get started. Any questions on what we talked about so far, or homework questions? Okay. Let's continue where we left off. So, last time we were talking about, assuming we have a good sample, with a whole bunch of data, or a whole bunch of numbers in it. We talked about organizing the data in forms of distributions, and all the different types of distributions we talked about, like histograms, like dot plots, sudden wave plots, Pareto plots, frequency polygons, and so forth. That's organizing data, and then we talked about summarizing data in the form of reducing all those numbers down to a single number that captures something meaningful about your data set. So one thing that we want to capture about the data set is the center. And we talked about two different measures of center so far. We talked about the mean and the median. Both these are designed to capture the center to measure what the most typical number in your data set is. So with the mean, we said for that particular data set, whether it represents a sample or a population, you would add up all the numbers in that group and divide by the number of numbers. For the median, we said that to find the median, you sort all the numbers in order, either lowest to highest or highest to lowest, it doesn't matter, and then you pick the number in the middle position. So that's the median. So let's compare the two measures of center. Let's say that we had a data set that was, let's say, a simple data set, simply the numbers 1, 2, and 3. And let's say that we wanted to compare the mean to the median. So for this data set, 1, 2, and 3, what would the mean be? Yeah, 2. And what would the median be? Also 2. Okay, good. So let's say that what we do now is, for this data set, we introduce what we call an outlier. So an outlier is a number that's very different from the current numbers, either much higher or much smaller than the existing numbers. So let's say that the outlier that we add is 100. So let's see how these measures of center end up changing. So let's do the easier one first. What would the new median be? Yeah, 2.5, because they're already in order, and the one in the middle position is the average of the two around that midpoint, which are the average of 2 and 3, which is 2.5.
53.
Okay, good. So the mean ends up being 53.
No, I just
No.
added that to you, what's wrong, it's
20 something. Right?
yeah.
26.5.
Okay, thank you. Okay, so the point is that you had these numbers that were very similar to each other in the data set, and then all of a sudden you introduce a number that is not representative of those numbers. That's an outlier. And every data set has outliers, and usually it's from measurement error, so that the number shouldn't be there in the first place, or maybe it's not measurement error, but it's just a number or a person that's just not representative, not typical in that group. So, which measure of center that's designed to gauge the most typical, the most ordinary number in that group, which measure of center do you think is more appropriate? Well, first of all, which measure of center is more resistant to this outlier?
The median.
Yeah, the median is more resistant because it's not changing very much as a result of this outlier. So we say that the median is more resistant to outliers. And conversely, the mean would be more susceptible to outliers. So which measure of standard do you think is preferred, being more susceptible or resistant to outliers?
More resistant.
Yeah, you would think maybe resistant just by how it's phrased, right? Because you're resistant just has a positive connotation versus susceptible. So being more resistant is usually preferred, so you would want to be resistant to outliers. So these are two different measures of center. That said, moving forward in this class and in statistics in general, anytime we try to measure the center of a data set, we're gonna use the mean. So that sounds like it's a contradiction from what we just said, because why would we use the mean if it has this less desirable property of being susceptible to outliers? So let's talk about that. So it turns out that the reason is largely historical, because calculators and computers haven't been around for a long time. And meanwhile, statistics has been around for much longer because it was designed to deal with human questions of uncertainty and try to quantify uncertainty. So of these two measures of center, the mean and the median, which one do you think is harder to calculate, takes longer to calculate?
Mean.
If you have a large data set, for example, and you had to do it by hand, which one do you think? Yeah, why the median?
Because you chunk on the points in between.
Yeah, but why does that take longer than the mean?
It's probably based on the frequencies or the weights and how many times it.
Okay, so let's say you had a list of lots of numbers, like a million numbers.
Did you have to add all those numbers up together to divide by the total number of data points?
Okay, so that's the mean.
Oh, okay,
And
sorry.
then the median, some of you guys are saying it takes longer, so why would the median take longer to calculate?
You have to put it in numerical order.
Yeah, right, so imagine you had a million numbers that are all in scrambled random order. To find the median, you would actually have to sort them first. And actually sorting takes a lot longer than just adding two numbers at a time and then dividing by the number of numbers. So it turns out that sorting is much more computationally complex. So it's gonna take a lot longer. So because of that, before computers and calculators have been around, people chose to build this framework of statistics around the measure of center that was easier to calculate. So arbitrarily, the mean was chosen, even though the median has more desirable properties in terms of outliers. Any questions? Okay, so some of you might be wondering, okay, so now computers and calculators are around, so why don't we just reframe statistics and start over? Why don't we just say that we realize the median has better properties, so we're gonna go back and restructure this this science, this art form, so that we're gonna recorrect our mistakes.
So you're saying, what are the lurking variables for doing that?
No, I'm basically saying, so moving forward, every time we have to calculate the center, we end up in statistics using the mean. But because it doesn't have this desirable characteristic of being resistant outliers, why don't we just change all our formulas that contain the mean so that it now involves the median instead?
I guess technically the mean would be more accurate. Like it's a more accurate number, even though the outlier knocked it off, the outlier's still there and you can't forget about it.
Okay, so maybe you do want to incorporate the outlier.
Right.
Okay, good. Who knows? Okay, good. So another reason is that outliers matter if you have smaller data sets. because the smaller the data set, the more the outlier will end up affecting that data set. But the larger your data set, the more the number of data points approaches infinity, then for every outlier that is high that you have, you're gonna have an outlier that's small that offsets it, that basically cancel out. So the larger your data set, it ends up, it doesn't really matter, the measure of center we use, because this issue of outliers takes care of itself. So that's one reason. And so in statistics, especially when we're looking at population data, we're gonna have a large number of data sets. I mentioned this distinction because a lot of times in real life, even though people as a whole deal with large data sets, you in particular might not deal with data sets that have millions of data points. So, for example, if even I look at a data set with a group of students, like 20 students, it's not gonna be millions of data points. So, if you're dealing with a smallish data set, then you're free to choose which measure of center you wanna use that's appropriate for that situation. You don't have to feel obliged to use the mean just because in statistics we talk about the mean over and over. So feel free to use the measure of center that's most appropriate for your application. So if you have a smallish data set that you don't want the measure of center to be affected by that outlier, then use the mean. But again, if you have a very large data set, then it doesn't matter which one you use. Okay, so that's the mean and the median as measures of center. And moving forward in this class, we're going to be using the mean to measure the center. So from your reading, what other measures of center have people used?
Mode.
Yeah, mode. And this is why in second grade you learn the mean, median, and mode all together, because they're designed to measure the same thing, which is the center. I don't know why second grade introduced this until it's actually appropriate to learn. But anyway, I learned it in second grade. I think a lot of people did it. So, what other measure of center did your book talk about?
Mid-range.
Okay, good, mid-range. So basically the mid-range, you guys remember really quickly. So mid-range is you're gonna take the smallest number of your data set, add to the biggest number, and then divide by 2. So it's just the average of the biggest and the smallest number. So you take the min plus the max and divide by 2. And so let's see what that's supposed to be doing. So let's say that you have a data set of grades, for example. And let's say that let's say you have all these grades that are clustered very tightly together. They're all around the 70s. And then suddenly you have these outliers. You have a 10 and you have a 90 here. So what would be the most meaningful measure of center? So if I ask you what the most typical grade in the class is, what should it be around?
70.
Yeah, it should be around 70. So the most typical grade should be 70, or the center of this data set should be 70. But one way to measure it is this mid-range, which is take the min and add add it to the max, and then divide by 2. So if you do that, you're gonna get 100 divided by 2, which is 50. So that 50 is gonna be, so that 50 is gonna be here. I was trying to make this to scale, but it's not. So the 50 is gonna be here. And basically what that 50 is the midpoint. So it's the data point that is the same distance from the min as it is from the max. So basically, this measure of center is giving you the midpoint between the min and the max. So it's only looking at the min and the max, and it's ignoring all these numbers in between. So do you think this midpoint is a good measure of center? No, so it's not typically a good measure of center, but it just allows you to calculate something that measures the center quickly by just looking at two numbers. Basically, it only looks at the min and the max and ignores everything in between. So if you want like a very, very rough measure of center, then people use this because it's quick to calculate. Okay, so of these 4, there's only 2 that are considered good measures of center, and that's the mean and the median. And the reason for that is because they use all the numbers in the data set to calculate these measures of center, versus the last 2. The mode only uses the most frequently occurring number, so you're only looking at one number in the data set, and mid-range is only looking at 2 numbers. So of these 4 that people have used to calculate the center, only 2 are considered good, and only 1, the mean, is used predominantly in statistics only because it's historically used, because it's easier to calculate. Any questions? Okay. So now that we've talked about measures of center, let's talk about something else we're interested in measuring. Which is what we call variation. So variation is a measure of how spread out the data points are from each other. So let's say that we have 2 data sets. Okay, so let's say we had 2 data sets, each one only having 3 values each. And let's talk about the measure of center that we've already talked about, which is the mean. So the mean for both these data sets ends up being the same. So the mean for both is 60. But just because the mean is the same doesn't mean the data sets are the same. Data sets are actually very different. So what makes the data set different are that the spread of the numbers are different between the data sets. So in the left, the data sets are clustered very closely together. The spread is low, versus in the second data set, the spread of the numbers is high. So we say that the first data set has lower variation than the second data set. So this says lower variation. So the question is, how do we quantify this? So a lot of times in math and statistics in general, we want to be able to put a number onto something that is intuitively obvious to us. So in this case, how would we take the three numbers on the left and assign a number to them that represents variation, so that number is actually lower than if we assigned a number for variation on the right? Yeah.
You're talking about class difference on this? For
No, I'm
example?
just saying that how do you quantify the fact that the three numbers on the left has lower variation? How do we assign a number for variation to the two sets of numbers?
I put it in ascending or descending order, however you want to present your data, and then it's the difference between each one, and whatever comes out to be the closest for the difference between them would be your mid-range between them or your difference.
So you're saying sort the numbers, like in this case, they coincidentally happen to be sorted already, and then you would find the difference between the numbers, like this. Okay, good, and then what? So how do you come up with one single number on most data sets that represents variation? So this is looking good so far, but so far we have not just one number.
Would you do the max minus the min? Like, same premise as the,
Okay.
do the highest number on each side minus the lowest number?
Okay, so let's hold off on this idea that we're exploring right now. Let's visit that idea first, and we'll come back to this. So let's say we looked at the biggest and smallest number and just subtracted them. So that's actually called the range. So if we look at the range for the first data set, that's going to be 1. And if we look at the range for the second data set, that's going to be 40. So in this case, this looks to be a measure of variation that works, because 1 is smaller than 40, so the left set of numbers looks like it should have lower variation. So this is indeed one measure of variation that people do use, called the range. So let's say that we had okay, so let's say that you had 6 numbers on each of these data sets. And now I ask you which one you think has higher variation as a whole. So which numbers as a whole are more spread out from each other?
The one on the right?
The other one on the right, as a whole, you have more variation, even though if you, on the left, if you're to try to measure that with a range and look only at the minimum and the maximum, then the range on the left is gonna be 98, but the range on the right is only gonna be 90. So if you try to use the range to decide which one has high variation, you're gonna be misled, because the range is only gonna look at the minimum max and nothing in between. So we want some measure of variation that is better than this, that is able to capture the behavior of the numbers in between as well, and not just the biggest and the smallest number. So yes, people do use the range to measure variation, but it's not a very good measure. So, any suggestions on a better measure of variation? Okay, so that's a very loaded term. What does that mean? Like, how does that relate to what we've already been saying? Okay, so let's build up, so the short answer is yes, we're gonna use standard deviation, but let's build up to that. So if you look at these data sets, let's say that we have this data set on the right here. Let me rewrite it. So.
You got 2 and 5 100.
Okay, so let's just look at one of the data sets, and let's see how we can actually quantify variation in a better way. So we said before that if you only look at the min and the max and subtract them, then you're ignoring all the variation or behavior of the numbers in between. So basically we're trying to measure how much spread or how much variation there is in general between all the numbers. So one thing we can do is what it's actually suggested before, is to actually find the pairwise distance between each of the numbers consecutively in between. And so the distance here, let's just call D1, just subtract the two, D2, D3, D4, D5. And once we have all these distances, then what might we do to ultimately have just one number that measures the typical distance?
Find the mean of D.
Very good. So find the average of all these distances. So that'll give you the most typical distance between all the numbers. So this is one good way that we could measure variation, is to find find the mean or the average of the distances. So the issue with doing this, well, can somebody think of a disadvantage of maybe doing this? So you actually mentioned it before, is that before you found these distances between every pairwise pair here, you would need to do what first?
Sort it
Yeah, why would you have to sort them first?
so that you can find the difference between each group from your, I don't wanna say this, well, however you sort the data for what your minimum and maximum is between each set that you're putting down, so you can find that difference.
Okay, good, because if we didn't sort them first, and then we just arbitrarily found pairwise distances, then the average distance that we end up finding would vary for the same data set for different arbitrary orders, right? And in the end, if we have the same data set, the same numbers, then whatever the order is, it should have the exact same measure of variation. So if we don't sort them first, then they're gonna have a different order, different measure of variation every consecutive distance that we take. So we'll need to sort first, just to make sure that we're gonna get the same average distance in the end. So that's a big issue, because we just said that finding the average is actually computationally complex. So that actually takes a long time. So even though this is actually a great suggestion, to sort all the numbers first, find the pairwise distances, and then take the average, let's try to avoid having to sort all the numbers first. So instead of doing that, what we're gonna do instead is, instead of finding distances between pairwise points, what we'll do is find the distance between a fixed point of each of the numbers. And the fixed thing that we're trying to find the distance for each of the numbers for, what would you suggest? Yeah, the mean, the average of the numbers. So the current center of all the numbers, which doesn't change no matter what the order of the numbers are. The center or the mean. And those will be the distances between each of our numbers. And once we find the distance of each number from the mean, then we take the average of those distances, and that'll give us a good measure of the average distance of each of the numbers from the mean. Any questions so far? Okay, so let's go ahead and find the average of these 6 numbers. Go ahead and punch and add the 6 numbers and divide by 6.
50.16 repeating.
50.16. Good, thanks. Oh, the 6 is repeating, or the 1 6?
The 6 is repeating.
Okay. Okay, so what we'll do now is we're gonna do exactly what we proposed, which is find the distance of each number from the mean, which we calculated to be 50.16 repeating, and then find the average of those distances. So the first distance will be the 9 minus 50.16. But if we do that, then are we gonna get a negative number or a positive number? Negative. So we know that this number represents a distance, which is supposed to be a positive number. So if it happens to be negative, we have to force it to be positive. And what's the mathematical operation?
Absolute value.
Absolute value, okay. So absolute value preserves the actual number and ignores the sign, basically forcing it to be positive. So then we would continue and do the same thing to all the other numbers. So the second one would be 18 minus 50.16 repeating, plus the next number, which is 27, minus 50.16 repeating. So I'm running out of room, so I'll continue down here. So each of these absolute values represents each of the distances from the mean. And then now to find the average, we're gonna add those up and divide by the number of distances, which in this case is 6. We're gonna be 6 distances. So this is actually a great measure of variation. However, this is not used in real life. So let's talk about why this isn't used in real life. So one thing is that you notice that there are all these absolute values involved. Anybody in this class taking calculus yet? No? Okay, so in that case, I'm going to explain it in a very overview kind of way. So later on, in other kinds of math classes, and especially in calculus, there are operations where if you have an absolute value, it actually makes that operation very messy. In calculus, in particular, there's this operation called the derivative that's actually very important, that's used throughout of other branches of math. And if you try to use that operation, the derivative, on an absolute value, it actually becomes extremely messy. So knowing that, we're gonna, while we're inventing this measure of variation, we're gonna try to avoid introducing something that we know will introduce problems later on. So in this formula, we're not gonna deal with this absolute value. So remember, the whole point of this absolute value was to force each of these distances to be positive. And so how else would we allow a value to be positive without using absolute value?
You need to multiply it by -1 to shift the sign, or do you do the inverse? I'm not sure where we're gonna go on that one.
Okay, good. So multiply by -1 is a good suggestion. However, basically that requires, for each distance you take, you have to check whether or not your number in question is less than the mean or not. And if it is less than the mean, then multiply by -1. We want something that we can apply blindly, no matter what the number is, without having to check it each time, and ensures that it's a positive number. Just like with absolute value, we don't need to check whether this is actually negative or positive. Absolute value will always make it positive. So what other operation could make a value always positive? Even though it might change the value, it'll always be guaranteed to be positive. So it turns out that if you square a number, it'll always be positive. So instead of taking the absolute value, let's instead square each of these. So this is actually a measure of standard, that's a measure of variation that is used in real life. This is called the variance. So you notice that in this variance, what we did was we squared each of the distances in order to force them to be positive, because distances doesn't make sense to have a negative distance. So because we squared each of the distances, now we just changed the meaning of this measurement. It's no longer the average distance from the mean, now it's the average squared distance from the mean. So the variance is the average squared distance from the mean. But we're not used to thinking in terms of average squared distances, because originally we wanted an average distance from the mean. So because we introduced all these squaring operations term by term, in order to offset that, what we end up doing then is taking the square root of the whole thing and calling it a new measurement, and we call it the standard deviation. So the standard deviation is actually the square root of the variance. So the standard deviation is an approximation of the average distance from the mean. So what do we say in an approximation? So if you if this is the actual value you're trying to find, and then you change it by squaring each of the terms, and then you take the square root of the whole thing to offset the squaring, does this equal the original? So let's go ahead and check. So the first one will be 6. The second one would be 1 plus 4 plus 9, which is 14. So this ends up being the square root of 14. Is that the same as 6? No. So the point is that that's what we did over here, is that originally we wanted to find the average, or the average of the stuff before we squared it. But then, as a result of squaring each term, we then took the square root of it to try to offset it. But you notice that it doesn't offset it completely. So these are actually different numbers. So that's why we say that after you take the square root of this, you're not getting the original average of average distance from the mean that you want, you're just getting an approximation. Any questions? Okay, so remember we talked about how every measurement that we talk about in the class will have a population component and a sample component. So let's summarize that. So let's say that we have a population and a sample. And let's say for each, we try to calculate the variance versus the standard deviation. So let's say that in our population, we have only 3 numbers, and let's say the 3 numbers are 2, 5, and 8. And let's say we also have a sample that is represented by 2, 5, and 8. But the meaning is different, because in the sample, we're assuming that out there in the world, there's a larger set of numbers that we actually care about, and we're just sampling from those set of numbers to get 2, 5, and 8. Versus in the population, we're assuming that these are the only numbers that we care about, the 2, 5, and 8. So we have these 2 separate cases. So let's talk about first the population variance. So first of all, let's talk about the mathematical symbol that's involved. So the population variance is given by sigma squared. So sigma is a Greek letter, looks like a lowercase o with a hook on it. So this is sigma squared. And this stands for the population variance. And so the way that we would calculate it is the same as before. We're gonna find the average squared distance from the mean. So if this is our population, then what would the mean be? Okay, I'll give you a little trick, is that if you look at the number that's in the middle, if it's the same distance as from all the other numbers, so 3 over here, 3 over here, then it turns out that the mean turns out to be the mean. So in this case, the mean is 5. So we want to find the average squared distance. So we'll take 2 minus the 5, square that, minus 5 minus square, 5 square that, or plus, and then plus 8 minus 5, square that. And then find the average of that square distance, so divide by 3. So we're getting 9 plus 9, which is 18, divide by 3, which is 6. So the average square distance of each of the numbers from the mean is 6. So that is the population variance. Any questions? So now let's look at the population standard deviation. So we said before that the standard deviation is just the square root of the variance. So we'll just take the square root of the variance. We said it was the square root of sigma squared. So what do you think the resulting symbol will be if it came from the square root of sigma squared? Sigma. So the symbol for the population standard deviation turns out to be just sigma. And sigma will be calculated as just the square root of sigma squared. So this will be the square root of 6. So the population standard deviation, which is approximately the average distance from the mean, is the square root of 6. Which turns out to be 2 point something.
2.45.
2.45. So the average distance of each of the numbers from the mean is approximately 2.45. And you notice that the actual average distance from the mean should be what?
3.
Yeah, it should be 3, because the distance from 2 to 5 is 3, distance from 5 to 8 is 3. But the distance from 5 to 5 is actually 0. So if you add up all those numbers, 3 plus 0 plus 3, divide by 3, you'll get 2. Right? So the actual average distance from these numbers from the mean is 2, but the standard deviation is telling us the approximate average distance. So you notice this isn't exactly 2, but it's close. Any questions? All right, so the approximate average distance from the mean is 2.45. So now let's look at the sample variance. So the symbol for the sample variance will be lowercase s squared. So s squared represents the sample variance. And the way that we calculate it is we're going to start just like before, where we're going to take the sum of the square distances. So here it'll be 2 minus the 5 squared plus 5 minus the 5 squared plus 8 minus the 5 squared. But now there's going to be a big difference, because instead of dividing by the number of distances, 3 in this case, we're dividing by that number minus 1. So instead of dividing by 3, we're dividing by 3 minus 1. So that happens anytime you're calculating a sample variance or a sample standard deviation. You're going to be dividing by n minus 1 instead of just n. So some of you might be wondering why that is. It turns out there's a very deep, important reason for that, but it's only like the 3rd day of class. So some of you might be really confused by the explanation. So I'll hold off on the explanation, but if you guys are really curious and you can't sleep at night until you hear the explanation, then see me after class, I'll be happy to tell you. Okay. So go ahead and calculate this s squared, or the sample variance. It's the sum of the square distances divided by 2 in this case. So we're going to 18 divided by 2, which is 9. So the sample variance is going to be 9. And then the sample standard deviation will be take the square root of that. So let's talk about the symbol first. So we know the standard deviation is the square root of its respective variance. So the square root of s squared, what symbol do you think people end up using?
S.
Yes, right. Because the square root of a variable squared is just the variable, so in this case it'll be s. So s represents the sample standard deviation, and in this case it's the square root of 9, which is 3. Okay, good. So for this data set, in one case representing the population, in another case representing the sample, each one has a variance and a standard deviation. And this is how you would calculate it by hand. And by calculating it by hand, we have an intuition as to what they actually mean. The variance means the average square distance. The standard deviation means approximately the average distance. So now that we calculated it by hand, you guys should also be comfortable calculating it using your calculator, where all you have to do is enter in the data set, and your calculator will internally use these formulas to calculate the variance and the standard deviation for both the population and the sample for you. So if you know how to calculate the mean for a data set, then you would use the same keystrokes, enter in your data, and then hit the stat variable calculation, and it'll give you a screen of all your stat variables. This might be instructive to go over for at least one calculator, just so you see. So every calculator is gonna be a little bit different. Even among Texas Instruments calculators, depending on what model you have, the keystrokes will be different. So, in general though, there's usually two modes on a calculator for statistics. One is to enter in your data, and one is to calculate the variables once you have entered in your data. So on this calculator, if you hit the data, there's a data button here where you can enter in your data. So once you hit the data button, there are different columns here that represent lists. So each list, you would enter in all values in your data set pertaining to a single variable. So for this case, if you have 2, 5, and 8, we're assuming that these values are coming from one variable that has these different values. So all the values that are coming from a single variable, you would enter into one column or one list. So in this case, we enter in 2, 5, and 8 into the first list. And just about this entire course will deal with one variable statistics. Only at the very end, if we have time, we'll do two variable statistics, but I'll let you know when that happens. So this will be, all these values are for one variable. So I entered in the 2, 5, and 8 in the first column, or the first list. And so after we're done with that, above the data button, in blue, it says stat, registers, or distribution. So then access that, basically we want to calculate the stat variables. So access that option by hitting second, and then data button again. And select one variable stats. And then it'll give you, and then make sure the defaults are correct. So the data was entered in list 1, or column 1, and then the frequency is 1, which means that for each data point that you entered, you're assuming that that occurs that one time that you entered. Alternatively, you can have a second list that for each data point you enter, you specify how many times that particular data point occurs. So you would put those frequencies in a separate list. But in this case, each data point that you've entered that one time only occurs once. So then calculate, and then it gives you a screen with all the stat variables in. So n is a good sanity check. If that number is correct, it gives you an indication that you entered your variables in correctly. So n is the number of data points, which is 3, which matches the 3 data points we have here. And then x bar is the sample mean, and indeed it's 5, like we expect. And so these are the next two that we need to look at. Remember, so on your calculator, it shows S of x and sigma of x. The x here is really redundant. It's just telling you that it's the sample standard deviation with respect to the variable x, and sigma is with respect to the variable x. So the x is redundant. But the S corresponds to the sample standard deviation that we talked about. So the sample standard deviation should be 3. And the calculator gives that, S is 3. And the sigma, which is the population standard deviation, should be about 2.45, but it's exactly 2.449 and so on. So the calculator is giving us these two values, the sample standard deviation sigma, or the population standard deviation sigma, and the sample standard deviation S. If you scroll down some more, you'll notice now you have other things, sigma x, which is the sum of all the x. If you add all the numbers up, you'll get 15. And so forth, but if you keep scrolling down, you won't see anything that corresponds to the variances. You won't see the sample variance or the population variance. So how do you think you could get those? if you wanted to know the two other ones that we have in our chart here, the population variance and the sample variance, 6 and 9 respectively, how do you think we could get those? The calculator is only giving us these two. How do we get the other two?
Square.
Yeah, very good, because we know the relationship between variance and standard deviations. The variance is just the square of the standard deviation, and vice versa. The standard deviation is the square root of variance. So if we have the standard deviation, we just square it to get the variance. Any questions? Okay, so every calculator is a little bit different. If you are wondering how to find the variance and standard deviation on your calculator, feel free to see me. Yeah.
So I have T13X. Is it necessary for me to get the one that you have?
No,
If
so,
I already have this.
yeah, so the keystrokes are just slightly different, but actually that calculator is pretty easy to use also, so I can show you after class or
I
whatever.
got it.
Oh, what is it? Oh, you got it. Okay,
Yeah.
that's fine. So yeah, you don't need to buy that same model. Okay. Alright, so any questions calculating these 4 things? Population and sample, standard deviation or variance? And again, all those 4 things are, it's just a measure of how spread out your data is. Okay, so of these 2 measures of variations that we talked about, both for the sample and the population, the variance and the standard deviation, which one do you think is more commonly accepted in terms of how people measure variation? Which one is used more, do you think?
Standard?
Yeah, standard because it has standard in it? Or what do you think?
Because I feel like it gives a more accurate results.
Yeah, it's more accurate in terms of what we want to intuitively measure, right? Because we're trying to measure the average distance from the mean, not the average square distance from the mean. So the standard deviation is closer to what we're intuitively used to trying to measure. So the standard deviation is more commonly used. So another reason why the standard deviation is commonly used is because it captures an important relationship between the percentage of the population that is within a certain number of standard deviations from the mean. So that was a mouthful. I'm going to give an example and then repeat that. So let's say that you have IQ scores which we've talked about before. And we said the IQ scores, if you look at the distribution of IQ scores, what's the shape of that distribution?
Bell shape.
Yeah, bell-shaped, very good. So it's bell-shaped, meaning the histogram is bell-shaped, and then if we connect the peaks of the histogram with a smooth curve, we'll get this bell shape. And let's say that we go out in the population and measure a whole bunch of people's IQ scores, and then punch those IQ scores in our calculator. Our calculator will tell us that the mean is 100, and the standard deviation is 15. So where this peak is represents the highest occurring IQ score, which is 100. So the most number of people in the population have 100 in their IQ score. And as you move away from 100 in either direction, fewer and fewer people have that IQ score. So it turns out that if you look one standard deviation below and one standard deviation above, one standard deviation below a mean of 100 represents what IQ score?
85.
85, good. Because one standard deviation is 15 IQ points, and going from the mean minus 15 will be 85. And then one standard deviation above the mean will be 115. So all these values between 85 and 115 represent values within one standard deviation of the mean. So all values within one standard deviation of the mean is between 85 and 115. So within, so instead of just writing out the word standard deviation, because the standard deviation of the population is represented by the symbol sigma, I'm going to use 1 sigma for one standard deviation. So within 1 sigma from the mean. And the mean, I'm going to use the symbol mu for population mean. So these values represent values within 1 standard deviation from the mean. And it turns out that there's an important relationship between all values that are within 1 standard deviation of the mean, because it turns out that those values also constitute an exact percentage of the population that has those values, and that exact percentage is 68%. So all these values end up constituting 68% of the population. And it turns out that I didn't just make up these numbers. Anytime you have any variable that's distributed as a bell curve, then this relationship is true, in that all values within 1 standard deviation of the mean end up being 68% of that population. So in this context, this is saying that 68% of everybody in the country has an IQ score between 85 and 115. And it turns out that any variable that's distributed in a bell curve, like heights, like weights, like standardized test scores, and so on, would have this relationship. Any questions? Okay, so it turns out that any fixed number of standard deviations within the mean also have a fixed percentage associated with it. So if we go 2 standard deviations from the mean, so instead of saying within 1 standard deviation, I'm going to say, just to save space, I'm going to say the mean plus or minus 1 standard deviation. And then all values within 2 standard deviations of the mean, or the mean plus or minus 2 sigma, first of all, let's make it concrete. So what's the lower bound for all values that are within 2 standard deviations?
7.
Yeah, okay, so 70 and then 130, yeah. Because if we start at the mean and we subtract 2 standard deviations, we're subtracting 30 points. So 100 minus 30 is the 70, and then 100 plus the 30 will be 130. Okay, so all values within 2 standard deviations of the mean, it turns out that that constitutes 95% of the population. So that means that 95% of everyone in the country has an IQ score between 70 and 130. That's almost everyone. And then it turns out that if you were to continue a fixed number of standard deviations from the mean, you'll have this fixed percentage associated with it. So let's do one more just for demonstration. So it turns out that all values within 3 standard deviations of the mean in a bell curve happens to be 99.7%. So in this context, what would be the lower bound of 3 standard deviations?
55.
55. So 55. So if you start at the mean of 100 and you subtract 3 standard deviations or 45 points, then 100 minus 45 is 55. And then what about the upper bound?
145.
Yeah, 145. So 100 plus 45 is 145. So in this context, that means that everyone that has an IQ score between 55 and 145 constitutes 99.7% of everybody in the country. So that's just about everybody. Any questions?
How do we find the percentages? It might be a simple answer, but how, is it like a chart or is it something we can calculate that percentage?
Yeah, so this, good question. So this percentage is mathematically calculated. This bell curve actually has a mathematical function associated with it, and we can find the area under this bell curve using a mathematical approach using calculus. And so either you can use calculus to get these numbers. We don't expect you to know calculus, so there's a table that's actually filled in for you from somebody who has done the calculus, and you can use that table to get these same percentages. But for now, we'll talk about the table later in the future, and again in excruciating detail. But for now, I just want you to appreciate that there's this relationship between the number of fixed standard deviations from the mean and how there's a relationship and a fixed percentage associated with that. Okay, any questions? All right. So in this case, this relationship only applies to bell curves. So only in a bell curve do you have within 1 standard deviation that percentage is actually 68%. If you had a different distribution, like for example, in a bell curve, this is 1 standard deviation from the mean, and you get 68%. But what if you had any other shaped distribution? What if you had a distribution with this shape, and you were looking at values within 1 standard deviation? Let's say 1 standard deviation is here. Do you think these values would constitute 68% of the population if it looked like a different shape?
No.
So here, this is 68%. But yeah, if it's a different shape, then you're no longer guaranteed the same percentage anymore, right? So that leads us to the next idea, which is can we extrapolate this conclusion about what the percentage should be if we know what the fixed number of standard deviations is from the mean? I.e., if we know that we're one standard deviation from the mean, 85 to 115, can we conclude a fixed percentage if we don't know what the actual distribution is, or if the actual distribution is different from the bell curve? So that leads us to the next idea, which is, let's say that you have all these measurements that represent something of interest, and then you punch all the measurements in your calculator. Your calculator gives you a mean measurement, and let's say the mean is 50. And your calculator gives you a standard deviation. Let's say the standard deviation is 10. And let's say that you're interested in knowing what percentage of the population, so not just the sample that you collected, but the whole population, so what percentage of the population has values so to avoid confusion, I'm going to say that just the mean, and really it's the mean of the data points you collected, so really it's a sample mean. And you want to know what percentage of the population has values between 30 and 70. So let's say to answer this question, you plot the histogram of these data points that you just collected. And the histogram looks like this. So this is for the sample you collect, and assuming it's a good sample, then you reason that the population probably has this distribution as well. So this looks like a bell curve. So because it looks like a bell curve, how would you answer this question? Percentage of values between 30 and 70, with this mean and the standard deviation. So if it's a bell curve, then you can use this relationship we talked about. So what would the answer be? Okay, why do you say that?
Because you do two standard deviations both ways to get to 30 and 70 from the sample mean of 50.
Okay, excellent. So going from 50 to our endpoints, 30 and 70, we basically ask, between 30 and 70, that constitutes how many standard deviations from the mean. So one standard deviation is 10 units. So since we have 20 units in either direction, that constitutes 2 standard deviations each way. So this is, you're adding 2 standard deviations, going from 50 to 70, and over here you're subtracting 2 standard deviations, going from 50 to 70. So all these values between 30 and 70 are within 2 standard deviations of the mean. So then we use this rule that we talked about for bell curves, that all values within 2 standard deviations of the mean constitutes 95% of the population. So to answer this question, all values within 30 and 70 are 95% of the population. Any questions so far? Okay, so let's say we have the same data, mean is 50, standard deviation is 10, and let's say that we plot the histogram, and it looks like something like this. Or if I were to do the bars. So this definitely isn't a bell curve, but we still want the answer to the same question, which is what percentage of all the data has values between 30 and 70. So that leads us to the next idea, which is something called Chebyshev's theorem. So Chevy Chef was a Russian mathematician, not to be confused with Chevy Chase. Tough crowd. So Chevy Chef's theorem gives us the answer to this very question, which tells us the percentage of the population within a fixed number of standard deviations from the mean. So this says that the percentage of the population within k standard deviations of the mean. The answer to that question is at least 1 minus 1 over k squared. So k represents the number of standard deviations from the mean, so what should k be here?
2.
Yeah, k is also 2, so all these values are within 2 standard deviations of the mean, so k is 2, so all we do is plug in 2 for k here, so we'll get 1 minus 1 over 2 squared. So 2 squared is 4, 1 minus 1 over 4 is 3/4, so this will be 3/4, which is 75%. So that number, 75%, is only one important part of the answer. The second important part is this qualifier of at least. So this is acknowledging that because we don't know what the distribution is, this actually works for all distributions. We don't know what the specific distribution is, so we can't say exactly what the answer is, but we know that the answer is at least 75%. So we're giving a lower bound. We know that the answer can't be less than 75%. So for any distribution, all values within 2 standard deviations of the mean can't be less than 75%. There can be anywhere from 75% or more. Okay, so let's say that you had gathered this data, mean is 50, standard deviation is 10, and you wanted the answer to this question of what percentage of the population has values between 30 and 70. And let's say that you first answer this question using Chebyshev's theorem, and you get the answer is at least 75%. Cannot be less than 75%. And then later on, you have some more time, so you actually plot the histogram out, and you see that the histogram is actually a bell curve. And so then you end up concluding that the answer is exactly 95%. So is there a contradiction in these two answers? The at least 75% and the 95% for the bell curve.
Chebyshev's theorem can be used for all data sets, but when you have a bell curve, they have more studies and data behind it that says this is what it is if you are within those limits, using the empirical rule. The empirical rule between the bell curves where Chebyshev's is general, so it's not gonna be accurate because it has degrees of variance or inaccuracies that are already accounted for.
Okay, excellent. So there is no contradiction. Chebyshev's theorem applies to all distributions. However, because it applies to all distributions and it's more general, it ends up giving us a less specific answer. However, this bell curve rule is much more specific and is able to give us a specific answer, but it only applies to bell curves. So if you use Chebyshev's theorem and get the answer is at least 75%, and then later, if you discover it's actually a bell curve, the answer is exactly 95%. Well, 95% is at least 75%, so there's no contradiction.
The only difference that I can see is what you'd use for, it's either equivalent to or it equals. That's the only difference that I really see there.
Yeah. Okay, good. Any questions? All right. So let's practice a little bit. So let's say that our sample mean is 30 and standard deviation is 5, and we want to know what percentage of the population has values between 10 and 50. And let's say that we don't know what the distribution is, and because we don't know what the distribution is, we cannot assume that it's a bell curve. So then what's the best conclusion that you can give?
The best I can give you is 75%. Can't say it's a bell curve and it doesn't meet the 2 standard deviations. So
Okay,
10
good.
10 is 2, but 50 is 4, so I've gotta figure out where that would be. There's a difference between what I'm setting there.
Okay, so it turns out that 10 is 20 units away, right? So it's also 4 standard deviations.
Okay, no chat.
So it'd be 1 minus 1 over 4 squared,
So it'd be, the answer would be at least
so
1 minus 1 over 4 squared.
15/16.
Yeah, 15/16, and if you punch that in, that's it. Yeah, 94%. So the answer is at least 94%. It can't be less than 94%. It could be 94%, it could be 99.9%, whatever the actual distribution is, but it can't be less than 94%. So this will be at least. And again, the way that we got that was we went from 30 to the endpoints. One is 10, one's 50. And going from 30 to 50 is 20 units. But we want to ask how many standard deviations is that. So there are 5 units for each one standard deviation. And if there are 20 units, then that means 20 divided by 5, that's 4 standard deviations. So we're adding 4 sigma to one end. And then same thing going from 30 to the lower bound of 10 is also 20 units or 4 standard deviations. So all these values are said to be within 4 standard deviations of the mean. And because of that, k, the number of standard deviations from the mean will be 4. So then you just plug in 4 for k, and this will be, the answer will be at least 1 minus 1 over 4 squared. Okay, so this will be 1 minus 1 over 4 squared, and it's at least that. So that's why we're getting at least 94%. So this is another reason why the standard deviation is commonly used, is because there's this relationship between giving you an idea of spread. So the more standard deviations away you are, the farther away you are from the mean, and the more of the data has been captured. So if you're 4 standard deviations away from the mean, then you've captured a lot of data. So you've captured at least 94% of the data in the population. questions? Okay, I think we're good for today. Have a good weekend, guys. See you next week.
Okay.